Hello everyone, welcome back to 4250. I'm your instructor, Dr. TJ Hammond. We'll again be continuing on with Chapter 4, Laser Oscillation, Gain and Threshold. These are lecture notes for Wednesday, September 30th. So what are we covering this week? Remember, we're talking about the amplification and stimulated emission part of a laser. So this is kind of like the main the crux of the point of a laser. So A, amplification, we want to make something very, very bright. SE stands for stimulated emission, as in we want to create these photons in phase, which is one of the main reasons why we like lasers rather than, say, just using a light bulb, where a light bulb is incoherent light. We'll, of course, be dealing with what coherent light means later on, but for now, just recognize it's not kind of random like a light bulb is. So this week we're dealing with amplification by stimulated emission. So the daily assignment, if you haven't yet, make sure you justify the equations 4.4.1 in your textbook or 3.12.5 and see if they're right. We'll be talking about them again in a few slides. So if you remember from before, what are the requirements for a laser? Well, you need to have some gain medium, something that can convert an energy source into something that's usable in some usable light source. So we pump this thing, so we apply some energy to this gain medium, and then that gain medium emits light in an area in the region, the energy region that we're interested in, and these photons come off in all directions. And what we need to do to make sure that this actually acts as a laser is something that provides feedback. And so these excited electrons, or these excited states, end up emitting photons in all random directions. But if we put mirrors on either side of this, then these photons that end up emitting along this path, this horizontal path, these photons will be trapped, and as they oscillate back and forth, they'll further produce stimulated emission, and they'll cause this positive feedback to allow for a laser to work. So what we found was the threshold gain. So the minimum amount of gain that you need in order to have steady state, where if you remember, steady state is when the intensity of this laser isn't continually fluctuating. So like if you had a pen laser or something like that and you're shining that across the room, you want to see kind of like a stable intensity spot on the far side. So that's when it's in steady state. And we said the gain threshold for this to work is when it's -1 over 2L, where little l is the length of this gain medium, times the log of R1, R2. But when R1 and R2 are close to 1, which is pretty common for lasers, so this mirror here is like 99% reflective, or 0.99, and this mirror here is 95% reflective, or 0.95. And this log of 0.99 times 0.95 ends up being close to 1 minus R1, R2. Okay, so this light rattles around within this cavity. As it propagates through this gain medium, it becomes amplified, hits this mirror, some of that light gets transmitted, and the amount of light that gets transmitted is the amount of the number of photons that get transmitted, or the number of photons that hit this mirror, times T2, times the transmission coefficient of this mirror. But a lot of these photons get reflected, and so that I plus times R2 get reflected, and these travel to the left, and these get further amplified in this gain medium here. So mathematically, what does that mean? We have the continuity equation here. So the continuity equation is actually, if this were equal to 0, so we'd have the number of photons coming into this medium is equal to the number of photons coming out of this medium. And that's what this is saying here is the partial derivative of the intensity, or the number of photons traveling to the right with respect to space, plus 1 over c, so 1 over this velocity, times the partial derivative of the number of photons traveling to the right over time. In just some free space, this would be equal to 0, because you'd have the same number of photons going in as the same number of photons going out. But then because we have gain, because this gain medium is being pumped and we have a whole bunch of electrons or atoms here in an excited state, we can actually extract energy out. And so the number of photons then leaving here are going to be more than the number of photons that come in, and that's going to be this related to this gain times the number of photons. So that's the number of photons going to the right. And then we'll have the same thing for the number of photons going to the left, but in the first term, because this is with respect to space, and these photons are traveling to the left here, these ones are going to the left, we get a minus sign because we have a minus z, but then everything else looks the same. So if we sum these two up, we sum all the photons that are traveling to the right and all the photons that are traveling to the left, we end up actually with a difference in the number of photons with the derivative with respect to space plus this 1 over c, and then the time derivative of all the photons. So all the photons traveling to the right is I plus, or that's the intensity to the right, and all the photons traveling to the left, or the intensity to the left, is going to be I minus. So the total number of photons, or the total intensity within the cavity, is going to be I plus I minus. And then we also get the gain times all the photons, or all the intensity in this cavity. Now, if there's a little difference between the number of photons traveling to the right and the number of photons traveling to the left, which is going to be pretty common, a pretty common occurrence, especially if the reflection of this mirror is pretty close to the reflection of this mirror, then that means this I plus minus I minus is going to be close to 0. So in that approximation, then that means that 1 over c, the partial derivative with respect to time of all the photons, is going to be approximately equal to the gain times all the number of photons. Okay, so that's what we get here for this photon rate equation. We'll skip some of this derivation, but the rate of change of the number of photons, or the rate of change of the intensity within the cavity, is going to be proportional to the amount of photons we're getting out of the cavity, so that's related to the gain, and then also related to the loss. So this, it takes c over 2L for one round trip. So the photons have to go, they have to travel to the right through the cavity length L, and then travel to the left cavity length L. So they travel a total distance 2L, and this is a rate equation. So in order to have this be some rate, we need c over 2L. And then we get the amount of loss per round trip is 1 minus R1 times R2. So this is made up of 3 terms where the rate of change of the intensity, or the rate of change of the total number of photons within the cavity, are going to be is going to be related to the gain that we get out of this gain medium, and then minus the amount of loss that we get that's caused by the mirrors. And we'll just assume that all the loss is caused by these mirror surfaces, but of course we have scattering, we have, we can even have absorption in the gain medium, we can have absorption in the air, a bunch of other things. But this is just some simple ideal case that we can work with. Okay, so these are the photons that are adding in, or the intensity that we're adding into the cavity, and these are the photons we're extracting out of the cavity. So we've been talking about the intensity, or where the intensity is of course related to the number of photons, but this is going to be related to the number of excited states as well. So we also need to relate these photons to the number of excited states that are happening within this cavity. So we're pumping this gain medium with some energy, and we're exciting these electrons or atoms or molecules or whatever to some excited state. We'll call that level 2, and it sits in this metastable state for a while, and then a photon comes in and extracts energy out of this. And so now this state has dropped back down to level 1, and we get another photon come out. And this is the stimulated emission. This gain now, of course, the number of photons we can extract out is of course going to be dependent on the number of states we have, or the number of electrons or atoms or whatever that in this state N2, or in state 2, and so the number of these will be N2, minus the number of electrons or atoms or whatever that are in ground state, or N1. So that difference will be related to the gain. But it turns out that the probability of this photon interacting with this electron isn't necessarily 100%, and the relationship between, or that that proportionality or that probability of this interaction of this photon and this electron is given by the cross section. So this is basically telling us how likely this photon hits this electron. And so that's a cross section. So you can kind of think of, it's like, say, a classical example would be like if you're shooting a basketball, it's like, what's the probability of you getting the ball in the hoop? It's like, well, it's related to the cross section of the hoop. If the hoop is bigger, then this cross section is bigger and you're more likely to get the ball in the hoop. And if the hoop is smaller, then the cross section is smaller and you're less likely to make a basket. And if you're like me, even though I'm tall, I'm terrible at basketball. So the cross section of a hoop is not nearly big enough for me to be good at basketball. But if we can now relate the gain that we've been talking about for this photon rate equation to the number of states that we have that are going to be excited within this system. Okay? So recall from last week, we were talking about spontaneous emission, that we were looking at what is the rate of this spontaneous decay, and we saw that this spontaneous emission rate is related to the number of states, the number of electrons or atoms that are in this excited state, so N2. So the rate of change of that is proportional to the number of atoms or electrons that are in this excited state. And so that's this dN2 by dt is equal to negative AN2. And now, of course, the number of electrons or atoms that are in the ground state will be related to that, to the number of electrons that were in this excited state, and the rate that they're decaying back into N1. And so that's given here as dN1 by dt is equal to plus AN2. Okay. Now, what we want to do to finish off this recording, I will try and relate the population rate equation to this intensity rate equation. So I've been saying that the intensity is related to the number of photons, so the number of photons is phi, and then the energy of each photon is h bar omega. So this is that relationship between the intensity and the number of photons. And so the equation that we had before for the photon rate equation is given here. Well, that's just given here, but that's in terms of these numbers of photons. Okay? And now we want to look at what the number of, the ground state atoms or electrons and the excited state atoms, but what do these depend on? So, of course, it depends on the pumping rate, so how fast we can change the population from N1 to N2. So if we pump this really hard or we provide this with a lot of energy, then it's more likely that we can get something into this excited state. Of course, it's also related to this absorption rate. And so it's how likely we can pump and excite from N1 to N2. So it's not only how much energy we deliver into it, it's also dependent on how likely it is that it absorbs that energy and converts that to an excited state, N2. It also depends on the cross section, so that also depends on how likely it is for a photon to stimulate another photon to drop back down to from N2 to N1. So that determines stimulated emission. And it also depends on the spontaneous emission rate. So I talked about how likely we are to absorb photons, how likely we are to absorb from the pumping photons, how likely we are to interact with other photons. And it's also related to how likely it is that this excited state N2 drops down to N1, like we just saw in the previous slide. It's also related to other things like collisions. So when you have, say, two molecules or atoms collide, they can cause spontaneous emission. That's less likely in, of course, something that's a solid. But if you have a liquid or a gas, you can have these atoms in these excited states for a really long time, but then they end up colliding, and then that causes some kind of spontaneous decay. So looking at these states, we have the rate of change of N1 is going to be, we lose these electrons or these atoms out of this system just by this gamma 1. So it's just kind of, these get excited to something that isn't involved with the laser. And then we have the stimulated emission. So we have this absorption cross-section, or the stimulated emission cross-section, sorry. And then we have the number of photons, so I over h bar omega. And then, of course, it's related to the difference of these two states. And then we also have spontaneous emission here in the third term. So as the N2 spontaneously decays down to N1, we get more states in the ground state, and so this is plus. Okay, now for N2, we also have the rate of change of the states of the number of electrons or atoms in the upper state will again depend on some kind of loss, something that doesn't involve this laser transition. We again get the spontaneous emission, or sorry, the stimulated emission term, but of course the sign is opposite because the if the stimulated emission is strong, then of course we lose electrons or atoms in the upper state, and they decay to the lower state. So we lose electrons here, so this is minus. And spontaneous emission, the same thing. We also have a minus here because when we have something in the upper state and it spontaneously emits, we lose that population in the upper state. But it also depends on this pumping rate, K. So if we pump this really hard, then we can have more atoms or electrons in this upper state. Now, if we convert these things to actually all be related to one another, then what we're trying to do is look at the number of like excited states and photons. So it's kind of like the excitations. So N2, of course, are excited states, and you can think of photons as some kind of excitation within the system. So because it's some kind of extra energy in the system, just like N2 is some electron or atom that's in an upper state, it's something that's excited within the system. So we'll call N2 and phi by C these number of excited states or number of excitations. And it turns out that if you add dt of N2 and d by dt of phi by C together, you get a spontaneous decay rate, which is this gamma 2, which, as I said, this is something that doesn't involve the laser transition, but you have A21 where you go from N2 down to N1. So this is some spontaneous decay rate. You have C over 2L, so remember this is related to the round trip time, and then 1 minus R1, R2, this is the round trip loss, and then this is the number of photons. So this is how many photons you leak out of this system. And then you have K, which is this pumping rate. And so that means the number of excitations in the cavity is the number of excited states, and photons, phi, depend on the pumping rate, K, the transmission rate, or like this loss rate from the mirrors, and this decay rate, which is some spontaneous decay. But it turns out that if you actually look at these, you have this G L over L phi, and you have C L over L G phi here. And so, of course, we're dividing C by phi by C. We get out that these two things are the exact same. And it turns out because we're pumping from state 1 to state 2, this absorption here, so this gain here, has to be exactly equal to the gain that we have of these photons. And so what that means is that the rate of these excitations doesn't depend on the stimulated emission or absorption. It depends on the pumping, but it doesn't depend on the absorption. And this is a problem, okay? This means that we can't actually create more N2, we can't have a higher N2 than N1. And that's because this gain here, or this absorption cross-section here, is equivalent to the absorption cross-section here. So what we need is for these two things to be slightly different. And so how we make those different is by having 3-level or 4-level laser schemes. So instead of just having 2 states involved, we need to have 3 states involved. So this will be it for this lecture. We'll probably be getting to 3-level and 4-level lasers on Friday, or maybe the end of Wednesday's lecture. But I just wanted to try and emphasize that if we just have level 1 to level 2, then it means that if we have atoms or electrons in this excited state, and then we have this laser transition, we can't actually get population inversion, because once we have more population in state 2, then we end up increasing the stimulated emission, and it just comes down to state 1. And so it's actually it's impossible to have in the steady state population inversion. So what you need to do is trick the system into having some other third state involved. And that third state involved ends up making these two gains slightly different. And so then that allows you to have population inversion. Okay, so we'll get more into that in the lecture tomorrow and on Friday. But hopefully this will give you a brief overview of what we're trying to cover this week in lasers.